Hello everyone, welcome to our lecture on analog electronic technology. In this session, we will continue our study of field effect transistors and their amplifier circuits by examining the small signal model analysis method. Today we will learn the small signal model analysis method. While we already know that the graphical method offers many advantages, it also has clear limitations. So today we will study another highly effective amplifier circuit analysis technique, namely the small signal model analysis method. Because a field effect transistor is a nonlinear device, establishing a small signal model involves approximating that nonlinear device as a linear one under specific conditions, thereby simplifying the analysis and design of the amplifier circuits built around it. Hence, the creation of a small signal model is of great significance. What, then, is the approach for constructing the small signal model? When the input signal amplitude is relatively small, the characteristic curve of the MOS transistor in a small region around its quiescent operating point can be approximated as a straight line, allowing us to treat the MOS-based amplifier circuit as a linear circuit. This is the essence of the small signal model analysis method, and the MOS transistor's small signal model is the circuit representation of the linearized characteristic curve. Next, using an N-channel enhancement mode MOSFET as an example, we introduce the model building process. Assuming the MOSFET operates in the saturation region and neglecting channel length modulation, lambda equals 0, we express the gate-to-source voltage in the characteristic equation as the sum of its DC component and its AC component. Grouping the DC value and constant term together and expanding the square of this binomial yields three terms. The first term corresponds to the static drain current. The second term is the product of the transconductance and the AC gate-to-source voltage, reflecting the linear relationship between drain current and gate-to-source voltage. And the third term is the square of the AC gate-to-source voltage, which gives rise to nonlinear distortion. Under small signal conditions, namely when the change in gate-to-source voltage is much smaller than twice the difference between the quiescent gate-to-source voltage and the threshold voltage, the square term's effect is negligible compared to the first-order term and can be ignored, and G sub M times V sub Gs is the AC component of the drain current. Observing this expression, we note that it characterizes a purely AC relationship, describing the voltage current behavior in the AC path, and that it captures how the MOSFET's gate-to-source voltage controls the drain current. In this way, we can use a single model to represent the port characteristics of the field effect transistor. At the output port, the drain current is described by a dependent source, a voltage-controlled current source, VCCs, with current flowing from drain to source, while the input port is the gate-to-source control voltage. This is the MOSFET's small signal model. Note that because the gate is insulated, the gate-to-source port is effectively an open circuit. If channel length modulation is taken into account, lambda is not equal to 0, then an output resistance R sub ds appears at the output port. As previously discussed in our treatment of MOSFET characteristic curves and equations, this resistance can be calculated, where 1 over lambda equals VA, the early voltage. In the model, the low-frequency transconductance is the slope of the tangent to the transfer characteristic curve at the quiescent operating point. Meanwhile, the output resistance R sub ds is the reciprocal of the slope of the output characteristic curve at the quiescent point. Therefore, under certain conditions, this linear model provides an approximate equivalent to the MOSFET's actual port characteristics, and the small signal model greatly facilitates dynamic analysis of amplifier circuits. However, special attention must be paid to the following points. First, the MOSFET must operate in the saturation constant current region and under small signal conditions for the model to be valid. Second, the two parameter elements in the model are AC or small variation parameters. So the model applies only to the analysis of AC signals or variations and cannot be used to analyze the static operating point. Third, both parameters depend on the location of the quiescent operating point. Different Q points yield different parameter values. Fourth, the current direction of the dependent source G sub M times V sub Gs is linked to the polarity of the control voltage. In other words, if either reference direction is changed, the other must be changed accordingly. Fifth, the small signal model does not include the effects of junction capacitances and therefore cannot be used for high-frequency analysis. For other MOSFET types, the model is the same because from the transfer and output characteristic curves of the other three MOSFET variants, we can see that the two element parameters in the model share identical properties. They both reflect ratios of variations and their slopes are positive. Let us now examine an example. A common source amplifier circuit with known MOSFET parameters and circuit values. First, we determine the circuit's static operating point. Then, under small signal conditions in the saturation region, we calculate the voltage gain, input resistance, and output resistance. Because the parameters of the small signal model are established based on the quiescent operating point, the static operating point must be determined before analysis. First, we open circuit the capacitive branch to obtain the DC path. Using the voltage divider formed by resistors R sub G1 and R sub G2 along the DC path, we calculate the quiescent gate-to-source voltage as 2 volts. Next, assuming the MOSFET operates in the saturation region, we use the characteristic equation to compute the quiescent drain current as 0.8 milliamperes. And from the output loop we find the quiescent drain-to-source voltage to be 1.88 volts. This confirms that the MOSFET meets the saturation region operating conditions. Next, to solve for the dynamic parameters, we short the capacitors and ground the DC voltage sources to obtain the AC path. Replacing the MOSFET with its small signal model yields the small signal equivalent circuit. Based on the quiescent operating point, the two small signal parameters can be calculated. G sub M equals 1.2 milliamps per volt and R sub ds equals 62.5 k ohms. Then, by formulating the input and output voltage expressions, we determine the voltage gain. Observing the input port, the input resistance is simply the parallel combination of R sub G1 and R sub G2. This shows that due to the gate voltage divider resistors, the amplifier's input resistance is no longer infinite. To find the output resistance, we short V sub I so that V sub Gs equals 0, which makes the dependent source 0, i.e. effectively open circuit, and the output resistance is then the parallel combination of R sub ds and R sub d, approximately 3.9 k ohms. The above demonstrates that, with a relatively small input signal amplitude, the field effect transistor operates within the constant current region of its I/UV characteristic curve. That is, the approximately linear region. The values of the model parameters are determined at the quiescent operating point. Therefore, the dynamic performance of the amplifier circuit is closely related to the position and stability of the static operating point. Analyzing the dynamic performance metrics of the amplifier, such as voltage gain, input resistance, and output resistance, using the small signal model is very convenient and also applicable for high-frequency analysis. The drawback is that in the small signal equivalent circuit of the amplifier, all voltages, currents, and model parameters pertain to AC variations, and thus it cannot be used to analyze or calculate the static operating point. These are the key points for this lesson. Thank you.